Hello, my name is James Peebles, and I am a student at Duke University. In this Capstone project, I built a machine learning model to predict the net electrical energy output of a combined cycle power plant. My approach followed the complete modeling process from understanding the data through preparing it, training models, evaluating them, and then interpreting the results. The dataset contained almost 10,000 hourly records. Each record included 4 predictors, which were temperature, exhaust vacuum, ambient pressure, and relative humidity. The target variable was the net electrical energy output measured in megawatts. When I explored the data, the most obvious pattern was a strong negative relationship between temperature and power output. This made sense because higher temperatures reduced the efficiency of the plant. For data preparation, I split the dataset into 80% training and 20% testing. I also standardized the features so that algorithms sensitive to scale, such as regression or support vector methods, would perform correctly. The dataset was already clean with no missing values, so I could focus on modeling rather than heavy data cleaning. I compared 4 different algorithms. First, I used linear regression as a simple baseline. Then I tested a decision tree regressor, which can capture nonlinear relationships, but sometimes overfits. I also trained a support vector regressor with a radial basis function kernel to give more flexibility. Finally, I trained a random forest regressor, which is an ensemble method that often improves both accuracy and stability. To compare the models, I used the metrics root mean squared error and R-squared. Root mean squared error tells us the average size of prediction errors in the same units as the target. R-squared tells us how much of the variation in the target the model explains. The results showed that linear regression provided a solid baseline, but it was outperformed by the more complex models. The decision tree sometimes fit noise and was less stable. The support vector regressor performed reasonably well. The random forest had the lowest error and the highest R-squared, making it the most reliable model overall. Looking at feature importance from the random forest confirmed that temperature was by far the most influential predictor. Exhaust vacuum and ambient pressure also played meaningful roles, while relative humidity had less effect. This confirmed what I saw in the exploratory scatterplits, and also made sense in the context of how turbines operate. Because of its strong performance and interpretability, I selected the random forest as my final model. It delivered the best predictive accuracy, captured complex relationships in the data, and also allowed me to explain which features were driving results. Completing this project gave me a clear understanding of the entire modeling process, from raw data to actionable insights. I not only practiced the technical steps, but also learned the importance of comparing different approaches and selecting the one that best balances accuracy and interpretability. Thank you for watching, and this concludes my presentation for the Duke Capstone project.